Every legacy has its first chapter.
And this is ours. Hi, I'm Arunendra.
And I'm Arushi.
And we are Team Vyomagami, which translates to Celestial Explorer.
The name of our rover is Vyomi, and we are from JP Institute of Information Technology.
Team Vyomagami was forged through adversity. We began with no roadmap, no prototypes to inherit, and no certainty of success. Yet, through countless setbacks, sleepless nights, and unwavering determination, we transformed ambition into reality. As the first generation of rover makers at our institution, we are not just building a rover, we are building a legacy. At the center is our team lead, Utkarsh Gupta, who oversees the project. The team is divided into 4 primary domains: management and research, hardware, software, and science. Management and research is led by Areen Jain and I, Arunendra Singh. The hardware division is led by Akshansh, who oversees 4 subdomains: mechanical systems under Aditya Bhaskar, firmware division led by Parth and Aditya Bhushan, PCB motors and sensor division led by Devik and Prashant, and drone systems led by Sridhar. Moving on to software, this is led by Anisha Roy and Harsimran. This domain includes autonomous systems and dashboard development. Finally, the science division is led by Shreyash and Anshul. Together, these domains form the heart of Team Vyomagami.
European Rover Challenge is one of the most prestigious competitions in the space robotics and innovation. For our team, it's not just a competition, it's more than that.
We are not falling apart, we are creating a path. Every challenge we overcome through, every innovation we build, and every milestone we achieve lays the foundation for the future generation who will follow.
That inspire generation of engineers to dream bigger, build better, and explore further.
I, along with my team, have designed the rover in which we are using a 6-wheel rocker bogie suspension with differential at the top, which is best for the challenging terrain of European Rover Challenge. The suspension legs are made of 2-inch mild steel pipes, giving structural integrity and also providing approximately 35 centimeters of ground clearance for tasks like drilling and handling weight of collected regolith and rock samples, which are essential part of ERC. Chassis of the rover, which is made of welded mild steel cage to withstand the weight of the components along with robotic arm. The chassis is 66 by 50 by 23 centimeters to facilitate good packaging and also providing enough breathing space to each and every component, as well as maintaining stability on tough terrain. The differential consists of 12 mm rod ends, which provides us resistance to any sudden jitter damage to the setup that the rover might feel by absorbing the shock. Have 20 centimeter diameter. They are made of TPU 95A with Z grip patterns to give the wheel resistance to wear and tear, but also ensuring optimal grip levels on slopes, sand, and mud.
For rover locomotion, we are using Rhino 24 volt 60 RPM motor, each providing 160 kg centimeter continuous torque and up to 360 kg centimeter peak torque. These motors are driven using BTS 7960 motor drivers, which are suitable for handling high current loads. Our main power source is ProRange 6S 22.2 volt 16,000 mAh LiPo battery, which provides enough power for our drive systems and other subsystems. For the robotic arm, we are using Rhino i32 12 volt geared motor rated at 60 RPM and 40 kg centimeter torque, which gives us controlled and powerful movement for our arm joints. For the drilling mechanism, the Y-axis motion is handled by the NEMA 17 stepper motor with a 310 mm lead screw, allowing us a precise linear motion. The rotation is done using a 775 DC motor, which provides high speed rotation required for drilling.
Our subsystems consist of two 6S 22.2 16,000 mAh LiPo battery packs, which are connected in parallel through XT90 connectors, giving us a total of 32 mAh at 22.2 volts nominal, which is sufficient for extended field operations. This feeds power into a custom power delivery board, which distributes power across 3 voltage domains. The first one being a 22.2 volt power rail, which directly powers the BTS 7960 driver motors. The second, a buck converted 12 volt rail for our arm, servos, and pumps. The third one being a buck converted 5 volt rail for our microcontrollers and our sensor peripherals. Finally, a latching mushroom head emergency stop button connected in series with the battery, ensuring a full system cutoff independent of the software.
In ERC, we'll be using ROS2 as it helps us manage and control different tasks very efficiently. A rover has many subsystems like navigation, sensors, cameras, robotic control arm. ROS2 helps all these modules communicate smoothly because of the modular architecture and makes our task more organized.
For a rover, we are using a decentralized compute architecture to separate high-level processing from physical execution. A central Jetson or an NX handles the heavy ROS2 and navigation tasks, while the small low-level tasks like the drive system, arm kinematics, and precision sensor polling are done by teensy microcontrollers. Each teensy microcontroller runs micro-ROS and uses its built-in Ethernet to communicate with the main board through a central switch. This clean separation ensures fast response times and precise control across the system.
Our drone is designed to perform stable autonomous flight along with real-time onboard vision processing. It also uses a lightweight carbon fiber structure to prevent vibration during flight. For flight control, we are using Pixoc flight controller. It handles stabilization, waypoint navigation, sensor data processing, and autonomous flight control. It also ensures reliable and precise control throughout the mission. For onboard computing, we are using NVIDIA Jetson Orin Nano Super. It provides AGI capabilities required for autonomous decision making and visual data processing. The drone also uses R2CAM camera module for capturing visual data required for target detection and navigation. The Jetson and Pixoc communicate through the Mavlink protocol, allowing high-level commands to be executed smoothly. This enables intelligent and efficient drone operation during the mission task.
Our navigation architecture is divided into three major layers. The first layer is the mission planner, where the rover analyzes terrain maps and computes the safest and the most optimal route using algorithms like Dijkstra and TSV. It evaluates terrain slope, roughness, and obstacles before the mission begins. The second layer is the navigation executive, built on ROS2 NAV2 stack. This layer converts waypoints into real-time motor commands while dynamically avoiding obstacles using LiDAR and depth cameras at a 10 to 20 Hz update rate. The third layer is localization, where we use an extended Kalman filter to fuse GNSS, IMU, and wheel encoder data to achieve highly accurate rover positioning even in rough terrain. To improve final checkpoint precision, we also implemented RUCO-based visual docking, allowing the rover to switch from GNSS navigation to camera-guided alignment for sub-meter accuracy. Our entire system is deployed on the Jetson Orin NX using ROS2 Humble and has been validated through simulation, hardware testing, and Marsyard-style terrain trials. Along with the rover side autonomy stack, we are also maintaining a real-time monitoring dashboard on the team side. The dashboard stack is built to stream telemetry, localization coordinates, sensor health, and mission statistics from the rover for live visualization and operational analysis. The communication pipeline is designed using ROS2 topics integrated with a web-based dashboard stack, enabling the ground team to monitor rover state, debug failures, and analyze mission performance in real time during ERC operations.
For the astrobiology subdomain, the work revolves around a clear, hands-on approach to find and analyze organics in the retrieved samples. One of our methods is thin layer chromatography. By carefully preparing our extracts, we let them rise up gradually on the silica plates. We can thus take complex unknown organic mixture and visually separate them out into their individual parts. From there, we move on to targeted chemical analysis for finding out basic building blocks of life like amino acids and proteins. Few examples for the same include tests like ninhydrin test, Biret test, and others. They include methods of preparation of the solution vials, adding suitable reagents, and hot water bath, etc. We also have the capability of testing for the pH levels by utilizing our pH sensing kit. Ultimately, to properly analyze biosignatures, we need to look at their unique spectral bands. This is why we are also planning on acquiring a suitable Raman spectrometer so that we can do the same. This would give us way better capability to quote the compounds detected with utmost confidence.
Our primary objective begins with a regional geology analysis of Eastern Hellas Planitia Basin. Using JMARS and Google Earth Pro, we process orbital data to define a landing ellipse that is both physically safe for the rover and scientifically valuable. From there, we build a detailed geological map of the Marsyard. We outline the boundaries of all visible geomorphological features and assign them relative ages, establishing the baseline for our field operations. The core of our field trial is testing a falsifiable hypothesis. We will use the rover's camera during the traversal to locate geological interactions that either sustain or reject our interpretation. By actively scanning for unexpected standing objects and mapping our surface sampling locations, we provide the exact geophysical context our astrobiology team needs to evaluate the area for signs of life.